This date is the 9th of April 2026. The time now is 2:49 a.m. And let me say, the video is going to be very formal. In a way, so formal, it's going to get it right. But I have the time to do it now, so let's get it done. 1 second. So, we'll be on quantum superposition decay for quantum class complexity. Uh, the quantum, I have to learn how to read the sign notation. Psi. Psi is so, what does it say? It's not tracking this. So, kitchen. So, I'm trying to do this for microware. Which is a quantum computer on the class system. So, microware is M for Mike, Q for umbrella, K for kilo, of Oscar is the operating system. This name stands for the spirit of good and evil that connects nothing and everything, that binds all of us, all of them. That's what microware means. Where was I? So I'm gonna introduce you to the concept here, you guys. So you have a phase, or let me just speak to the camera. So you have a function, you have an algorithm, uh, uh, an algorithm on a Turing machine that is classical, based on Turing principles, which I'm claiming is which I'm formalizing as the read read write tape machine. So let's get to the point concept here. Quantum a quantum superposition is an entangled qubit, which is a classical bit, a quantum bit on a classical system, a quantum bit on a classical system, such that it possesses the uh, uh, superposition decay, a property of superposition. So superposition is the fundamental principle. The fundamental principle that uh, uh, okay, what's the solution? Let me ask my computer. Let me see if I can remember it. Nothing. I'm not cheating here. Uh, uh, what is superposition? What is superposition? Can be reached. My phone's connected and it can't be reached. Yeah, let's do a Copilot thing. Copilot. It's another principle of quantum that states linear combinations of solutions of Schrodinger equation and solutions of Schrodinger are also feasible. Yes. So, that must mean basically, in quantum mechanics, a linear combination of Schrodinger equation solutions, the wave postulate. Yes, yes. So you get the wave postulate, you get the transformation for this. Psi equals C1, psi equal 1 plus P2 psi 2 C2. The theory of quantum postulates that wave complexity determines the state of the quantum system of any time. Furthermore, this differential equation is represented by linear and homogeneous conditions that are met with two solutions of wave function, psi 1 and psi 2, as the linear combination of the solution of the wave function. So basically, there's many ways to do stuff, and the money can resolve kind of a fast way. So in a duality of state, uh, uh, duality of state, such as wave and particle, a wave function can be evaluated by a wave postulate. Now, the wave postulate is the core principle that determines how a wave function collapses. The superposition is a property, is a fundamental principle, a guiding principle that dictates what how the wave function collapses, or how does the wave function follow a probabilistic cycle graph on a quantum system. Um, Quantum wave function can be solved using the position of psi vector r, or wave function momentum, and psi p, where the position motivation and solutions. So transformation function is what changes the collapse wave function via the wave postulate. The probabilistic direct cycle graph is a computational model for the same thing on a classical system. The most resolved quantum. This video was primarily on quantum field, quantum algorithms, quantum class complexity, quantum class complexity. Let me go to my notes. Such that we have superposition decay. So a quantum system can decay, which is why the postulate matter. Because until you measure a power system, you are taking information, you're getting results, trying to measure results. And I'm claiming that R, the radius of system, is waves are two or more constructive deconstructed electron. Yeah. Superposition only holds in linear systems. I'm reading this and I'm not yet. So you have, like my analogy was stemmed from the concept of uh, measuring all probability at once of a system, which was a probabilistic DAG. Now, the wave function can be mapped. One believing, one postulating is the wave function. Can a wave postulate, which is a subset of the theorem of the function of a wave function, can be mapped in a solution space of isomorphic to Turing complete machines. For example, the algorithms that for quantum field theory, no, algorithms for quantum superposition is the for quantum systems that obey linear principles, and linear growth such that there is a way to define a kind of mapping between the probability DAG and the state of superposition for a classical system. I am proposing the Turing machine, the evaluation of a quantum algorithm on a Turing machine is bound to a superposition decay. A superposition decay is the fundamental principle to understand how to take a measurement on a classical system and get a coherent quantum log of m. I'm trying to build quantum computers, yes, but I'm building them on quantum classical systems for now until I have quantum hardware to start building my hardware for the hardware. More specifically, I'm looking to formalize the probability DAG as a continuous, as a discrete, no, not continuous, as a discrete linear sequence of a linear sequence from point given 2 points A to point B in a system of so given a probability DAG, a probability directed static graph, we have to understand that there's a superposition decay when a measure is taken. For example, to connect to the internet, there is to connect to for example, define a connection string, define define a quantum connection Q equal to A and B. G equals to a quantum connection Q equal to a probability DAG E equals to directed a spectral graph. Okay, so the graph equals A and B. The graph UV, the graph the graph has an edge and a node, En, and to take a quantum measurement of a system to determine a connection string, you have to either apply quantum filters to determine one way. Okay, so I'm saying very formally that you have to understand there's duality. There's all quantum algorithms can be executed in parallel. All classical algorithms defined by a Turing machine can be executed in parallel by a quantum system. No, that's not true. I mean, let me frame that. All non-deterministic, all deterministic classical algorithms can be executed in constant time in parallel by a quantum system. That's the core premise of today. So the premise lies that there's a probability. Okay, let me write that again. All classical algorithms all classical algorithms that is bound by linear time complexity, very important, deterministic or non-deterministic, doesn't matter, can be measured, via a quantum system, via quantum superposition decay in parallel. This means that all problems that belong to the n non-deterministic some non-deterministic problems. Some all classical algorithms that bound by linear time complexity determined determined by all linear algorithms and some non-deterministic. Some. No. And yeah, all because they are linear sequences. So they can be evaluated as a linear system. All problems that can be mapped, all problems that belong to a set of linear equations, the linear system or system of linear equations can be expressed in parallel as a probabilistic directed cyclic graph on a quantum system. Superposition decay is a window of control and or collapse. Is a window of collapse, such that we so the window of collapse is like a system that presses a quantum some kind of a letting go, some kind of final outcome, a final opportunity to roll back the chain, to take the information into hand. For example, we have two reads, four writes and two reads, four writes, two reads. Equals one write, equals one read operation. When you use this is a model of having a read and counting system, based on quantum principles. Four writes and two reads are equivalent to one entire operation because the read comes last. This is a dual state, so so you can use this of solution too. So this time, because based on memory mosaic tables like R row and column, two-way tables such you get R on the read, Rx, and the column will be this machine forget this, guys. Main idea of superposition is to provide a framework with no entanglement, study superposition entanglement. Because Targumum requires a system that maps to the size function and the function function. Now, the wave function, the wave postulates are like triangular postulates. So, is the match? Think of them as matching or regular expression matching. I like to think of in language as regular expression matching. Such as RIRT, which is using to match systems of so you get basically Rift is the flex. Three stands for Rift is the flexible translator, and you can match streams of information in parallel because the computer allows for to use the syntax to register a grammar, which is a production rule. For example, if there's a production rule in lexicon analyzer. In a parser state, in a parser, the parser will have to evaluate how the system uses a parser to uh, so the system has to use a parser to evaluate state of ambiguity. For example, if I'm matching a parser x if I'm evaluating pi, no, let psi, let m be equal to 3. This is annoying. Let n equals 25, 34, 3, 6, 5, 9, 36. And then I print n divided by 2. Uh, STR, STR. So, example, I'm claiming that the superposition decay is a kind of final window that allows for rollback or no rollback change in a system for in the kind of quantum sense of the framework. A row R, read write row. This is one of the system. You can have read write execute per row and column that determines how a system can be coherently 100% certain about to certainty. The Rift is usually to match data cycle drop via this framework superposition. When a superposition state decay, you have the disjoint parallel computation of the algorithm that's computed apart, which are the calculus system, the define or the algorithm define. So an algorithm can be n linear time log n, which is half linear time, O of 1 constant time, and O of 1 constant time. But this can all be done in parallel if there is if they share a disjoint sequence of instructions that map in parallel to a instruction order that map in parallel to a system of whether a system is allowed to perform a 2-bit operation. Now, the 2-bit operation is like one is a 1 qubit operation via cube CUBIT, such that there's the computing can be done in parallel, and that's the same thing at one time. A situation window will allow this to happen because if a superposition states if a superposition states decay, there is room to a decay like quantum decay. Then you have two solutions that are separate but unhomogeneous. They can be mapped to each other. This is what I'm talking about the system. They can be mapped to each other in the classical sense and the quantum sense. QBP, quantum QBP, quantum burst protocol. Oh wow. Uh, Problems. I'm talking about not this one. Uh, Quantum. Okay, classical complexity. No, 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 no. So this adds annoying me. So system of a quantum system. The question wasn't a quantum state is literally represented by a state of superposition, and superposition decays. By decaying superposition, by decaying superposition, you're taking a quantum measurement, and you can there's a window that the quantum measurement allows you to connect or disconnect, and this can be bound to a cognitive system via stability as well. So via stability principle as well. So doesn't claim me here. Now I'm gonna demonstrate how this works via memory mosaic system. So that's what superposition is. So superposition is a system that respects the person nonlinear sequence or nonlinear based on probability directed cycle graph in a cloud system that resolve a measurement heuristic that is shared, which is the superposition decay, to resolve two sets of artifacts what I call 2 byte artifact. Let's go back. Let's go back. Via a superposition state. So there are two algorithms that solve the same problem and they can map to each other for use for different solutions. But they are optimal solutions because they're homogeneous based on type, not kind, not heterogeneous. That's what I'm saying this superposition is going to do. So you can define an algorithm with a class complexity, quantum class complexity. Quantum class complexity. Yeah, that's what I'm looking for. A quantum class complexity. Uh, a quantum class complexity is it's mapped to the algorithm defined in classical systems too. I'm you know this is the redirect. Oh my God. To the superposition layout. Let's find it here. I can't find the notation of a Newton's notation. Quantum class complexity. Defined by the problem space, there's a solution heuristic. This is solve the problem. Obviously, there's an algorithm, there's a pseudocode you can write for two systems that happen to one problem in quantum systems. And that problem space is a Venn diagram of the QBP layer. The two algorithms need to be when superposition decay as a measurement. As a measurement. So you're gonna have the P space promise-based space with a P space, and every string that restricts all strings of A. No. So we have promise space, uh, uh, P space of which are uh, map, which is the dimensional Turing machine with no problem in polynomial space. Polynomial or these still written as a polynomial or non-deterministic polynomial, which is basically a polynomial which is many terms at once. Accept every string in A yes and reject any string in all strings in A no. In parallel, it's a promise. A promise is did you clean your room? I'll give you. A promise has three states: resolved, rejected, and pending. Now, the half promise problem is the PP complexity classes, which are the probability Turing machines that accept every promise problems which for which polynomial time probability Turing machine accept every string in A yes with a probability of greater than half, and accept a string every string of A no with a probability of most half. Now, this is where non-deterministic NP problems lie. That can be reduced to NP, reduced to P. These are PP problems, problems. This is a P-space problem. This is a PP problem. So this is a promise problem that resolve a time complexity of a non-trivial system of type two will be n quadratic n cubed n squared or n cubed n squared and above. Problems such that this is BQ. So my system can receive BQB problems. This is what I'm trying to do. BQB problems, promise problems such that the function A comma B is set of natural numbers, which implies 0 and 1. There's just a polynomial general family of quantum circuits Q equals Qm, such as n is an element of natural numbers, where Qm is a set of n qubits that gives an output to 1 bit. Yeah, this was talking about that accepts an n qubit and gives an output of 1 qubit. So this thing that the promise space of the system is this is what I was referring to. Anything above BQB is hard for a superposition decay to imagine. You multiple superposition decay, or different principles to address the promise space via the solution. The solution space accepts the circuit, the quantum circuit. Now, the quantum circuit is the configuration such as had mat X or C not gate that determine how the n qubit output a 1-bit system, a 1-qubit system. An element of X of yes is accepted by Q, which is probably greater than equal to A of X. An element of X is A no, which is accepted by probability less than equal to BQ, which means BQP is a promise problem. And this promise problem maps to functions that are homogeneous only. They only share one. The homogeneous problem that share two disjoint solutions in problem space. And anything BQB is not in that category. BQB is in this category. So all the problems of BQB, PP, and P space can be solved can be done effectively by a superposition decay, which is taking a measurement and allow a system to decay, like having particles in the duality of states or electrons. Doesn't matter what it is, as long as the window for decay, this can resolve to two solutions in a space in one of these class of spaces. BPP. Now, BPP is promise problems that for which the polynomial Polynomial probabilistic term machine accepts everything in A, yes, and with probability at least 2/3, and accept everything with B with probability 1/3. This is basically a harder problem that leads to heterogeneous data sets in a quantum state. And this quantum state accepts that strength of the data set, but anything above that is harder. So P problem is the hardest complete problem. Problems which are polynomial determined by Turing machine. Accept all yes or just also of no, which is P problems. So P problems, BQ problems are part, but NP completes our problems are not part of BQ problems. So you can take a superposition decay and manage the kind of problems here in kind of a space here. Thank you for watching this video. This is my diary. So let me just take this. I don't suffer with autism. I don't suffer with anything. Okay, thank you for watching this video. Quantum physics. Let me stop this video now. Thank you for watching this video, guys.